Hi everyone. In this lecture, we'll try to derive transfer functions of second order lossless systems or circuits here by inspection. Okay, we have already done that for passive RL circuits, passive RC circuits. So now we are going to do for passive LC circuits. Okay, and mainly we are concerned about second order systems, meaning they'll all have poles, they'll all have poles on the j omega axis. They'll be of this form: h of 0 into 1 plus s by omega z square and 1 plus s by omega z. You'll have a complex 0 or you'll have a complex pole, that is purely imaginary poles. You'll either have zeros and poles on the j omega axis. Okay, so we'll see how to do that by inspection for any given LC circuit. So for this circuit, I'm applying input at this point and output, I'm taking the output across the capacitor. So you're supposed to derive the transfer function. So first you have to find the DC gain, which is h of 0. So we know an inductor behaves like a short circuit at DC and capacitor behaves like an open circuit. So the circuit just reduces to this. So Vi simply equals V0, so the DC gain h of 0 is 1. The next thing is to see if the circuit has 0. So we'll apply the same principle, wherein first I'll call this impedance, I'm going to compare this with the standard impedance Z1 and Z2. This is the model we have used in one of the previous lectures to find poles and zeros for RC circuits. We'll apply a similar procedure for LC circuits as well. So to find the 0, I'm going to equate Z2 to 0, and the condition is Z1 should not be equal to 0 at the same time. The other condition is Z1 should be infinity and Z2 should not be infinity at the same time. So applying these two conditions, I can find the zeros in the circuit. So when will Z2 become 0? Only at infinite frequencies. When omega is infinity, the capacitance behaves like a short circuit. So at that point, you have output to be 0. So again, that's not a practical finite frequency, so we'll ignore that. And Z1 will become infinity only at omega equal to infinity. Okay, so therefore the circuit doesn't have any 0, so I can ignore that. The next thing is poles. To find the poles, I can short the circuit the input and equate simply Z1 equals minus Z2. Using that condition, we can get the poles. So I can simply short circuit the input and find the impedance, point at which this impedance blows up. So that will be SL equals minus 1 by SC. So S square equals minus 1 by LC. Okay, and the poles are complex purely imaginary, which is plus minus. So in this case, the poles would be plus minus J1 by root LC. Now when you have a transfer function, but this is nothing but omega naught, this is plus minus J omega naught. Omega naught is 1 by root LC. So if I apply this in this equation here, so I'm simply going to get 1, there is no 0 in the circuit, by 1 plus S square LC. Okay, so this is one quick way of writing it. Or you can also see that at very high frequencies, this function reduces to 1 by S square LC. So we can also see that from this circuit I can easily get that at very high frequencies the impedance of a capacitance will become very small. Okay, so if I have two impedances like this, the impedance of the capacitance, this is Z2 and Z1, the impedance of the capacitance Z2 is going to become very small and Z1 will be very large. In that case, the simple voltage division becomes Z2 upon Z1. It's actually Z2 by Z1 plus Z2. I can ignore Z2 in comparison with Z1. So it will be simply the ratio of two impedances. Whenever one impedance is much smaller compared to the other, we can simply use this relation, Z2 by Z1. So Z2 here is capacitive impedance, which is 1 by, so I'll just repeat that point. So when you have two impedances of this type, Z1 and Z2, so when Z2 is much less than Z1, I can use the approximation, the ratio of two impedances, the transfer function will be approximately equal to the ratio of the two impedances, Z2 by Z1. So in this case, it's Z2 is a capacitor, so the Z2 is 1 by SC, and Z1 is an inductor, so it is SL, so you get 1 by S square LC. So it matches with this, and the DC gain again of this is 1, so both are met, and it doesn't have any 0 in the circuit. And we also saw that the pole is actually a purely imaginary complex pole. So this is the transfer function. The transfer function is shown here. Now similarly, we'll do it for other circuit. So in this circuit, to find the transfer function, again this you can see that the h of infinity at very high frequencies, you can see the DC gain, or you can find the DC gain. At DC, the capacitor behaves like an open circuit, and the output at this node will be 0 because inductance will also become 0. Okay, the impedance of the inductance will be very small, the impedance of the capacitance will be very high. Okay, so you have a condition where both the impedances are going to act in such a way such that both will actually give 0 at the same point. So for example, I'll use this condition to find, all I'm saying is if the DC gain, first to find the DC gain, capacitor is in series with the input, so all the input in the steady state will fall across the capacitor, so therefore DC gain is 0, and at very high frequencies capacitance will behave like a short circuit. Okay, we can just draw the circuit for DC and high frequencies. At DC, the capacitor is an open circuit, inductor is a short circuit, so the output is 0. At very high frequencies, when omega is infinity, capacitor will act like a short circuit, inductor will act like an open circuit. So your VI will be equal to V0, so V0 will be equal to VI, and H infinity equals 1. High frequency gain is 1. So we can see that this is some kind of a high pass filter because the low frequency input gain is 0 and high frequency gain is a constant. So to derive the transfer function, first to find the pole, it's very simple. I can simply short this input and equate it. So you get the pole at same location, which is S square equals 1 by LC. So there are two complex poles here, minus 1 by LC. Okay, and so the pole is fine. So that is, the denominator is easy to write, which is 1 plus S square LC. Now is there any 0 in the circuit? Okay, so to find the 0 in the circuit, we'll apply the standard method. So first we try to find when does your Z2 go to 0. Z2 can go to 0 at omega equal to 0. At that point, we just have to ensure that Z1 doesn't go to 0. Okay, at DC, inductor impedance becomes 0, which is fine, becomes very small. Inductor impedance becomes very small, and capacitor impedance becomes very large. So this condition is met. So there is a 0 there at DC. At the same time, I'll use the other condition, which is Z1 equals infinity. The capacitive impedance becomes infinity at omega equal to 0, and Z2 is not equal to infinity at that point. Z2 is also equal to 0. So there are two zeros, and both of them are occurring at the same point. So using both the conditions, both the conditions, in this circuit, it's telling you that both these conditions are going to, are feasible at omega equal to 0. Okay, both these conditions will be satisfied at omega equal to 0. So therefore, which means you are going to have two poles, two zeros at DC. To write the transfer function at DC, I'll just use this condition that your impedance Z2 is very small compared to Z1. So therefore, I can write the transfer function simply as Z2 by Z1. So it will be SL by 1 by SC, which is S square LC. At low frequencies, I can ignore this term. So it will simply reduce to 1, the denominator. So the transfer function should match this at low frequencies, S square LC. So I'll simply write the numerator as S square LC. Okay. So this is, if you're going to have a 0 at the origin, okay, so how do you find the coefficient? How do you find the coefficient here? I'll just use this condition. In this case, it was satisfied. Or by looking at the circuit, you can actually predict what will be the low frequency gain. You can, most of the times you can actually very easily write it by inspecting the circuit itself. Okay, so if you remember in RC circuits, whenever we had a 0 at origin, we used to use the condition that for low frequencies, capacitor has a very high impedance, so most of the voltage will drop across this. So the current generated in the capacitance is VA into SC. That when flows through an impedance of SL, that will be your V0. So the transfer function for low frequencies is S square LC. So which is true here. Okay, so this is S square LC by 1 plus S square LC. So we actually saw that there are actually two zeros at S equal to 0. Okay, both these conditions were satisfied, okay, at the same frequency. So that should give a hint that there is actually there should be more than one 0 in the system. So then we'll analyze more complicated circuits. So for this circuit, first we'll find the DC gain. So to find the DC gain, At low frequencies, inductor will behave like a short circuit, capacitor will behave like an open circuit. So the circuit will reduce to, so whenever you have an inductor and capacitor in parallel, at low frequencies this will just behave like an inductor, okay, omega tending to 0. At high frequencies this network will simply behave like a capacitor. The lower impedance will always dominate when two elements are in parallel, okay. So we'll use that, and we can say that at low frequencies the circuit will simply reduce to two inductors in series, and the gain here you can simply write h of 0 as half. The next thing is to find zeros. Now to find 0, I'm going to use the condition. First condition is Z2 equal to 0. Z2 becomes 0 at omega at DC. At omega equal to 0, the inductor impedance becomes 0. But you should see that at the same frequency, this impedance, the tank, the LC parallel LC circuit impedance will also become 0. Right? It's just an inductor and capacitor in series, so it will behave like an inductor at low frequencies, which is going to be 0. The impedance is going to be 0. So therefore, that condition cannot be used, because your Z1 is actually equal to 0 at the same point, so you can't use this condition. The other condition is Z1 become infinity and Z2 should not be infinity at that point. Now Z1 is actually a parallel LC tank. A parallel LC tank or LC circuit, we know that this impedance will become infinity at the resonant frequency. We already plotted the impedance in the previous class. So at SL equals 1 by SC, you will minus 1 by SC, you are going to have this impedance blowing up. So here it's clear you are going to have a purely imaginary 1 by LC, purely imaginary, this is minus 1 by LC, so S will be plus minus J 1 by root LC. So you are actually having a purely imaginary zeros, two zeros, okay. We can see that since this is a finite frequency, the impedance of this Z2 becomes infinity. Z2 becomes infinity only at omega equal to infinity. So this is a valid condition. Okay, we can use the second rule to find the 0. So we found there are two complex purely imaginary zeros in the circuit, and the DC gain is half. And one other thing is just to find the poles. So again, like we discussed in the RC circuits and RL circuits, when you have just one capacitor and many inductors in the circuit, you can still say that circuit will be like a second order system, will behave like a second order system, a lossless second order system. Okay, there should be no resistors, purely just one capacitor and many inductors. That circuit will behave like a lossless second order system. Again, you use the same logic. If you can write, so for example here there are two inductors and one capacitor. So ideally you're supposed to have a third order. It can be a third order. The maximum order can be 3. But you can actually write a linear relationship between the voltages across the two inductors. There is a linear relationship between the voltages across the two inductors, because of which the order will be reduced by 1. Okay. So similarly, if I have a circuit which just has one inductor and many capacitors, okay, even that will be a second order systems, because all those capacitors, even though there are many, most of the voltages across the capacitors, all the capacitor voltages will be linearly related. Okay, I can reduce this entire capacitor to a single equivalent capacitor. Okay, so then the complex poles seen, the complex poles omega, I can write it as, or the square of the complex poles will simply be 1 by, I'll just write the magnitude, 1 by L equivalent into C equivalent. Okay, you have to just find the equivalent inductance at that point. If you have a single inductance, then L into C equivalent. If I have many inductors and just one capacitance, then C into L equivalent will give me the 1 by root of plus minus J will be the complex poles. So using that, I can very simply write here. So in this problem, this is L, so this is L, L and C. So I can simply write the poles as, I just have to short the input, so L and L will appear in parallel. So you are going to have L by 2, SL by 2 should be equal to minus 1 by SC, the impedance being equal, I mean Z2 being equal. This condition is satisfied when I use this Z1 being equal to minus Z2. So from this I can get the complex poles. So you can see complex poles will be plus minus, so plus minus J upon root LC by 2. Okay, so now I'm ready to write the transfer function. The DC gain is half, and zeros occur at 1 plus s square LC, okay, and the pole occurs at 1 plus s square LC by 2, okay. So again, as I said, this LC by 2, this term LC by 2 will be actually be L equivalent into C equivalent. So if I had a single inductor and many capacitors, it will be L into C equivalent. If I had a single capacitor and many inductors, then it will be C into L equivalent, okay, an equivalent of all those inductors seen by the capacitor. So in this problem, it is actually there are two inductors which are in parallel. The effective inductance seen by this capacitance C is L by 2. So the resonant frequency will be LC by 2, I mean the term 1 upon root of LC by 2. Okay. So this is SP. The omega P, the resonant frequency will actually be omega naught. I am going to use the term omega naught. So this is equal to plus minus j omega naught. So omega naught is actually equal to 1 by root of LC by 2. And we already said the transfer function is of this form, 1 plus s by omega naught the whole square, and you can just simply substitute it here, you will get this. Okay. So similarly for 0, I didn't mention it explicitly, but this is actually equal to plus minus j omega z, and so therefore omega z will be simply equal to 1 by root of LC. Then you can simply substitute this in the general expression that we have for which I have showed it in the beginning of the lecture. I will just write it here. So the general expression, which is h of 0 into 1 plus s square by omega z square by 1 plus s by omega naught the whole square. Okay, you can simply substitute it in this equation. Okay, so now that we have done it, we have spent a little bit more time on this one problem. So now we should be able to write it quickly by looking at this circuit. Now in this circuit, if you see, if you want to find the 0 here, first the DC gain first. At DC, the inductor will behave like a short circuit. So the DC, the circuit will reduce to something like this. Capacitor will behave like an open circuit. So Vi, your V0 equals Vi, so h of 0 is 1. Okay, so I'll ignore this. Now there is another quick way of seeing it, whether the circuit has zeros or not. So at high frequency, the gain should not be infinity. If the high frequency gain is finite, then we know that there is, of course, when it's a circuit composing of just L inductors and capacitor, you are going to have resonant poles at omega naught. Okay, but to know whether the circuit has zeros or not, your high frequency gain should be finite. It should be non-zero. Okay, so then you will know that you are going to have some kind of zeros, complex zeros in the circuit for a purely lossless circuit. So in this case, H infinity for high frequency, the circuit will simply reduce to two capacitors, because when parallel LC circuit will reduce to a capacitor at very high frequencies, so H infinity is actually equal to half. Okay, so we'll verify that once we write the transfer function, we should be able to verify this. But as I said, you just need one. If you know H of 0 and the pole and the resonant frequency and the complex 0, you can write the whole transfer function. You don't need to know H of infinity. Okay, because once you define H of 0, omega z and omega naught, H of infinity is uniquely determined by these three values. Okay, so first we have written H of 0, which is 1. Now the next step is to find the zeros. So in this network, to find the zeros, I'll simply use the condition when Z2 is 0. Z2 becomes 0 only at infinite frequencies, so I'll ignore that condition. And similarly, Z1 becoming infinity. That can happen at S equals plus minus J by S equals plus minus J by root LC. So this is actually a complex 0. So omega Z equals 1 by root LC. Now to find the poles, see there are two capacitors and one inductor in circuit, so you can just find the total capacitance, equivalent capacitance seen by the inductor. So the poles is simply going to be plus minus J by root of L into C equivalent, in this case is 2C. The inductor will see the two capacitors in parallel, so you will have this. So now to write the transfer function, this is plus minus J omega naught, so your omega naught is 1 upon root of 2LC. So to write the transfer function, I just simply have to write it for the 0, which is 1 by S square LC by 1 plus S square 2LC. Okay, and H of 0 is 1. Now you can verify at very high frequencies, at infinite frequencies or very high frequencies, So this will reduce, I can ignore the term 1 in both the numerator and denominator because these terms will go much larger, will grow much larger. So this will be S square LC by 2 S square LC, so which is half. Okay, the high frequency gain is half. And we already showed that in this circuit it is actually half. Okay. Now in this circuit, you again for this circuit you are supposed to find the transfer function. So I'll very quickly write at low frequencies the capacitor won't matter. So it will simply reduce to a circuit like this, L and L. So H of 0 is half. And does this have a 0? 0 occurs at when this impedance becomes 0, and that happens either at DC. At DC inductor, this inductor impedance becomes 0, but this that too Z1 also becomes 0, so we can't use this condition. The other condition is when Z2 becoming infinity, and Z2 becomes in the second impedance. This one is Z1 becoming infinity. Z1 is the impedance in this arm, so this Z1 becoming infinity. Okay, that happens only at omega equal to infinity, so there is no 0 in the circuit. Okay, and we have to now find the poles in the circuit. So again, this is one capacitor and two inductors, so the omega naught is simply going to be 1 by root of C into L equivalent, which is L by 2. Both L will be in parallel. You just have to short the input and find the equivalent inductance seen by the single capacitor. So from this I can write the transfer function as half. There are no zeros in the circuit, and then 1 plus S square LC by 2. Okay, and we can easily verify at very high frequencies. If you look at this circuit, at very high frequencies the circuit will reduce to this inductor and a capacitor. There is no there is no the other inductor will not come into the picture because that impedance is going to be very high. And you can see very easily the gain of this circuit is 0 at very high frequencies. At very high frequencies this circuit transfer function will be simply Z2 by Z1, which is 1 by S square LC. This transfer function will reduce at high frequencies to 1 by S square LC by 2, which is again equal to 1 by S square LC. So which is same as this. So for this circuit, again when omega tends to infinity the gain is 0. So this is a low pass system. You can easily see that at high frequencies the capacitor will behave like a short circuit, inductor will behave like an open circuit. So you are going to have a circuit like the equivalent circuit like this. So V0 will be 0. So this is a low pass circuit. Again, in this circuit we are supposed to write the transfer function. At low frequencies the circuit simply reduces to capacitor and an inductor. Okay, so the larger the impedance, when two are in parallel, in the smaller impedance will dominate. So this will simply reduce to a circuit of this type. So at very low frequencies, if you remember when we derived for the high pass transfer function, we said the circuit will actually behave, the transfer function will be simply the ratio of this impedance. This is a very low impedance, and this is this impedance, which is a very high impedance. So it will be S square LC. You can also see that at omega equal to 0, the inductor impedance becomes 0. Okay, and the capacitor impedance is not 0. At the same time, capacitor impedance becomes infinity. Okay, and this is not infinity. So both the conditions are satisfied. So which means there are two zeros at origin, and that's what is captured here. The transfer function will be S square LC for this circuit. Okay, we already said it's the ratio of the two impedances, so you will get S square LC. This is because you know that there is a 0 at DC. Okay, the next thing is to find the poles. So there are two capacitors and one inductor, so I simply have to write it as 1 plus S square L into C equivalent. In this case it is 2C, so I'll write 2S square LC, and the numerator is going to be S square LC. If you look at this circuit, it's a high pass circuit, high pass transfer function. Look at this transfer function. At high frequencies H infinity is going to be, so this is the ratio of this term by this term, that's going to be half. So if I look at this circuit at very high frequencies, it will reduce to a capacitor C and another capacitor C. So this again H infinity is half. Okay, so we could write the transfer function directly by this. Okay, this is a high pass filter, it's a high pass characteristic. So you can see DC inductor shorts out, the gain is 0. So we know that, if DC gain is 0 and high frequency gain is finite, then it's a high pass characteristic. Okay, since it only composes of inductors and capacitors, so we are going to get a second order 0 and a pole transfer function like this. Okay, to find the numerator, I just tried to understand the behavior of the circuit at low frequencies and then wrote the transfer function directly. Okay, if you remember in one of the previous lectures, we also discussed we can write this transfer function by drawing the high frequency circuit, finding this value, okay, and initially assuming this as some value k, and then finding the high frequency gain in terms of k and equating it to half. We can do that as well, but this is just, you can choose whatever is comfortable to you. I prefer this because it also gives you the intuition what's happening at low frequencies. It behaves like a second order differentiator at very low frequencies. We saw both RL circuits and RL circuits and RC circuits, which have the first order high pass transfer characteristic, will behave like a first order differentiator at low frequencies. So whereas an LC circuit, a lossless second order LC circuit, will behave like if it has a high pass characteristic, they will behave like a second order differentiator given by this. Now this circuit, I'm trying to introduce a series LC branch, LC. So just to reiterate, we just mentioned in one of the previous lectures, if I put two impedances, Z and minus Z in series, the effective impedance is going to be 0. Similarly, if I put two impedances in parallel, Z and minus Z in parallel, the effective impedance is going to be infinity. It's going to behave like an open circuit. So using that, we have already, this is what we applied in the previous lectures to find, one of the previous lectures to find the poles and zeros in RC circuits and RL circuits. Now, we'll try further in this circuit and see what happens when you have a series LC element. So when you have a series LC element, so first, again, we'll first find the DC gain. For DC gain, this inductor will behave like a short circuit and the capacitor will behave like an open circuit. So the circuit reduces to something like this. So V0 equals Vi. So H of 0 is 1. Next is you have to find the 0. To find the 0, there are two conditions. One, the impedance Z2 becoming equal to 0. That happens when SL becomes equal to minus 1 by SC. This impedance here, when SL becomes equal to minus 1 by SC, a series LC circuit offers 0 impedance at the resonant frequency. Again, we already discussed this in the previous lecture. Okay. And the omega naught is going to be, this is actually, I'm going to call it omega Z, is going to be 1 by root LC. Okay. You're going to have two zeros at omega Z, j omega Z, and omega Z will be 1 by root LC. Okay. This can be found by equating the impedance here Z2 to 0. And when you do that, you actually get two complex zeros, okay, on the j omega axis, and the value of the 0 will be 1 by root LC. The other condition is when Z1 becoming infinity, and that happens only at omega equal to infinity, so you don't have a 0 there. The only 0 is this, okay, and it's a complex 0. Now the next thing is to find the pole. To find the pole, we'll again short circuit the input, and as I said, we can simply find the equivalent capacitance, equivalent inductance seen by the capacitor and take the product of the two. So in this case, it will be C into 2L. Okay. So 1 upon that with the square root will be your omega naught. Okay. So again, whenever you have a circuit composing only of inductors and just one capacitor, it's going to be a second order system. Okay. And similarly, when you have many capacitors and just one inductor, that will also be a second order system, a lossless second order system. And the resonant frequency can be simply found by finding the equivalent capacitance seen by the inductor or equivalent inductor seen by the capacitor. So from this, I have all the information to write the transfer function. I know the DC gain, omega z and omega naught. So the transfer function is going to be 1 into 1 plus s square LC. The 0 is accounted here, and then the pole, which is the resonant pole, which is s square 2s square LC. Now the high frequency gain from this circuit can be very easily seen as half, okay, the ratio of this term by this term. And from this circuit, if you draw the high frequency equivalent, only the inductors in a series LC circuit, only the inductor will matter at high frequencies. So its capacitor impedance will be very small, we can ignore it. Okay, since they are two are in series, the higher impedance always matters. So if you apply Vi here, your V0 is going to be half at high frequencies, and that's what we get from this transfer function. Okay. So similarly, I'm now going to add a capacitor in place of inductor, the same circuit. And for this, we'll try to derive the transfer function. So first, DC gain first. So the capacitor will behave like an open circuit. There are two capacitors in a series LC circuit. Capacitor, whenever you have inductor and capacitor in series, the larger impedance will dominate. So at DC, it's going to behave like this. So H of 0 is half. Next, 0, this impedance blows up, becomes 0 at omega z equals 1 by root LC. You're going to have a complex 0 plus minus j omega z, and omega z is 1 by root LC. You can just find it by equating SL equals minus 1 by SC, like we did in the previous problem. Then to find the pole, there are two capacitors and one inductor, so your omega naught is simply going to be 1 upon root of L into C by 2. Okay, effective capacitance seen by the inductor. So when you short the input and find the effective capacitance seen by the inductor, these two capacitors will come in series, so equivalent capacitance will be C by 2. Now we have everything to write the transfer function. So gain is half, 0 is 1 by s square LC, and the pole is 1 by s square LC by 2. Now from this transfer function, just to verify it, your H infinity is actually equal to 1, right? If I take the ratio of these two, you get 2, and that into half is going to be 1. And we need to check if it's 2 or not. At high frequencies, the gain is 1. So your capacitor, inductor in series, the inductor, you can ignore the capacitive impedance. So the capacitor is going to behave like a short circuit, inductor is going to behave like an open circuit. So the circuit will reduce to something like this. Okay. So your V0 will be equal to Vi. So your H of infinity is actually equal to 1. Okay. So we get that from the transfer function. See, we didn't actually compute H infinity, but still we were able to write the transfer function. So as I said, the DC gain, the 0 and the pole uniquely determine the transfer function. You don't need to know any other parameter. Okay, for this second order lossless transfer functions. So now we'll take a few more simple examples and try writing the transfer functions. So again, this circuit will reduce to C and C at low frequencies. So your H of 0 will be half. Okay, and to find the 0 in the circuit, either Z2 should be 0, and that happens only at infinite frequencies. Okay, at this point the series LC circuit will behave like an open circuit at infinite frequencies. So yes, I can use this condition, but it turns out that frequency is infinity, or Z1 should be infinity, and that happens at infinite frequencies again. So there is no 0 in the circuit. Next is to find the pole. So again, there are two capacitors and one inductor, so you can find simply L into C equivalent, which is L into C by 2. So the transfer function omega naught will be simply 1 by root of L C by 2. There are no zeros in the circuit. I mean, zeros are at infinity, so there is no finite 0. So the transfer function would be half into 1 by 1 plus S square L into C upon 2. So you can again very easily see the high frequency gain in the circuit is simply 1. That you can verify it here yourself. So that high frequencies inductor will behave like an high frequency the gain is 0. The high frequency gain is 0 in the circuit. Okay, at high frequencies the transfer function will simply reduce to 1 by S square LC. Okay, it's a low pass transfer function, and that you can verify in the series LC circuit. I can just replace it by the single inductor. The capacitor will not matter here, they both are in series. So at high frequencies, the capacitive impedance will become very small. So I can use Z2 by Z1, 1 by SC into SL. So it's 1 by S square LC. Okay. So and that matches with this. And we'll take another circuit. I'm just doing all possible transfer functions that you can get with passive second order LC circuits. Okay, and show you that we can very easily write the transfer functions by inspection. So in this circuit, again, you can see that this circuit, the gain, DC gain is 0, because your capacitor is going to be an open circuit, inductor is going to be a short circuit. So most of the input voltage will fully fall across this. So which means there is 0 Z origin. Okay. So again, Z2 will be 0 at origin. So I mean, when it's a lossless LC circuits, by now you know that whenever you have a 0, it's going to be it's going to be 2 zeros at origin. Okay. So this transfer function SL is I can reduce the circuit to something like this at low frequencies. Okay, capacitive impedance is much larger, so in the series LC it will be represented by a single capacitor. Now this transfer function we can write it easily as impedance of ratio of SL by 1 by SC, so it will be S square LC. So this is the low frequency transfer function. That you have to multiply it with the poles in the circuit. Again, the poles in this circuit, there is one capacitor and two inductors, it will be S square C into 2L. Okay. So the high frequency gain H infinity for this circuit is actually half. The ratio of this term by, this term upon this term, it's half. And that can be very easily verified here. It's just two inductors in the circuit. The capacitor impedance will be very small. So the DC at the high frequency gain is half. So we'll take a slightly more complicated circuit and then try to derive the poles and zeros for it. So again in the circuit there are three capacitors, but there is only one inductor. So this is again a second order lossless system. Okay. So now you are supposed to find the pole zeros and the transfer function for this. At low frequencies, inductor will behave like a short circuit. So this inductor will behave like a short circuit. So the circuit will reduce to something like this, 2C and C. And the low frequency gain H0 will actually be 2 by 3, right? So you have to find 2C by 3C, which will be 2 by 3. Now next step is to find the zeros. This Z2 in the capacitor here will blow up to 0 only at infinite frequency, so I can ignore that. Now this guy here will become infinity. They have to find when will that become infinity. That will become infinity when the parallel impedance blows up. That happens when SL plus 1 by SC, this impedance in this arm, should become equal to minus 1 by SC. So using that, I can say S square as minus, the condition whenever that impedance blows up, so this will be minus 2 by SC and this is S here. So S square equals minus 2 by LC, or S equals plus minus J root of LC by 2. Okay. So when you have a big network of impedance, you just need to find, it just has one inductor and many capacitors. You just have to find when it blows up to infinity, just find the effective capacitor seen by the inductor. Okay, you will get that value. So this is your plus minus J omega Z, and your omega Z is 1 by root of LC by 2. And to find the pole, I have to short the input. So the circuit is this, I have to short circuit the input and find the effective inductance, effective capacitance seen by this inductor now. Now the difference is these two capacitors will add up, so we'll have 2C, and that 2C will be in series with C. Okay, that will be the equivalent capacitance. So you would get the equivalent capacitance 1 by, the resonant frequency is going to be 1 by root of L. C equivalent in this case is going to be 2 by 3C. So we have all the variables to, all the values to write the transfer function. So DC gain is 2 by 3, and there is a 0 at 1 plus S square LC by 2, and the pole is at 1 plus S square L into 2 by 3C. So I'll write 2 by 3C here. Now again, The high frequency transfer function for this will be the ratio of these two terms. So it will be 2 by 3 into half by 2 by 3, which is half. So again, to find the high frequency gain, at high frequencies, this part, the inductor here, in this circuit, this is the circuit given to us. The inductor here will become an open circuit, so this part will not figure in. So the circuit will simply reduce to a capacitor and capacitor in series. So the high frequency gain is half for this, and that's what we get here. Okay. And finally, we'll write this LC, again L to C. So you can try to write the transfer function for this circuit. Okay, so here of course there are two elements here, but we can see that both the inductor and the capacitor voltages can be linearly related. So the order will be reduced by 2 in this circuit. Okay, so you can do a direct derivation of the transfer function and verify for yourself, and you can also try to find the poles and zeros in this circuit. So to find the zero, this impedance will blow up and this impedance should go to 0, and that happens only at DC or infinite frequencies. But this also goes to 0 and infinity at the same frequencies, so we can't use this condition. The other condition is when this impedance blows up to infinity, and that happens when S square equals 1 by LC, minus 1 by LC. Okay, so we have a 0 at plus minus j by root LC. Next thing is you have to find the pole. For that you have to just short circuit the input, group all the inductors together so that your equivalent inductor is L by 2 and capacitance is 3C. So it's going to be 3 by 2 LC. Okay, so that will be your L equivalent, C equivalent. So your omega naught is going to be 1 upon root of 3 by 2 LC. And the DC gain, you just have to reduce it to inductor and an inductor, L and L, because they are in parallel. Capacitors will not matter at low frequencies. Capacitor impedance is very high. The lower the impedance, that's going to matter. And the DC gain is going to be half. So now we are ready to write the transfer function. DC gain, the 0 here is 1 plus S square LC by 1 plus S square 3 by 2 LC. Okay. Now at high frequencies, H infinity of this circuit, of this transfer function is ratio of this term by this term into half, that you will get 1 by 3. So we have to see what happens at high frequencies in this circuit here is that the inductors will not matter because capacitor impedances will be very small. So it will be C and 2C. Now the transfer function for this at high frequencies is simply 1 by 3. It is C by 3C, which is 1 by 3. So that matches with what we wrote here. Okay, you can verify the transfer function yourself. You can find the whole transfer function and do Z2 by Z1 by Z2. You should get the same transfer function that's shown here. Okay, so I'll stop at this point. So the next lecture we'll probably go into series RLC circuits and try to model, try to see what happens when you have losses. So I'll stop at this point.